All right, so this is lecture 4.2, where we will continue talking about synthesis. Specifically, we're going to focus a little bit on the digital side. So there's not quite as much going on here, but a little bit that we'll do in the lecture. And then I'll give you some examples of some of the different both analog and digital types of synthesis that we've talked about so far. And then we'll finish off with a introduction into VCV-Rack and being able to sort of play through some of these concepts that we've looked at with analog synthesis in a digital version. So we'll go ahead and do that, and also do a quick introduction of the short assignment 3, and that will be 4.2. We're going to continue on with synthesis here and look into the digital side of things, whereas of course last time we were looking at analog. Again, we're going to change over and look at digital. Now with the digital synthesis, there's hardware and software synths that are digital. And a lot of this stuff really pulls from the same concepts that we learned with analog synthesis and this idea of modules. Now, a lot of times they may be set up with different, menus and arrangements of a lot of these things. Instead of actually using patch cables, you may end up seeing knobs and other types of things of that nature. But again, a lot of the same concepts. So let's quickly just do another simple definition here of digital synthesis. So as you would think, like we talked about the difference between analog audio and digital audio, digital synthesis is generally emulating the process of analog synthesis, but using electrical oscillations that are represented numerically. Remember, in analog, or rather digital audio, we had bits, zeros and ones that were representing those waveforms. Same thing is happening here. The oscillators are represented numerically. And within digital synthesis, a series of computational procedures called an algorithm is designed to shape the output. But again, based on a lot of the same concepts from analog synthesis. So here we're just going to kind of dig into some of the digital synthesis types. Since there's not a lot of extra information to go over here, we'll just sort of see where the differences lie here between analog and digital. So one of the big things that digital can do that analog cannot is called analysis-based synthesis. And this is when digitized sounds are analyzed with a computer to determine the fundamental frequency, partial content, and amplitude envelopes that are present, so as to reconstruct them with or without alterations. Now, within this analysis-based synthesis, we can have the same additive or Fourier synthesis that we had in the analog world, but in this case, we can have many more oscillators than were possible in analog, and this is used for something called resynthesis. Just like in analog, if we build a complex waveform with all these oscillators, the synthesis of a sound based on the analyzed info from another sound can actually be built up. So similar concept, but done slightly differently. We take, let's say, for example, we analyze a sample of a piano. And in that analysis, the computer goes through and figures out the fundamental frequency, the partial content, amplitude envelopes, all that stuff. And then maybe synthesizes a whole new sound based on some of those analyses, but then some of those could still be tweaked. So you may be trying to totally recreate that piano that you've sampled, or you may be taking specific things, maybe the partials, for example, and then applying those to some other amplitude envelopes or fundamental frequency to get different sounds. So there's this same sense of additive synthesis in digital, but because you work with it within this analysis based idea, you can resynthesize other things as well. Now, it's important to note that in this process, something called the fast Fourier transform is used to do the analysis and the resynthesis. Now, you don't need to know this transform. It's pretty intense math-wise. So really at this point, I'm just asking you to note that something called an FFT, or a fast Fourier transform, is what is used to actually analyze things like the partials that are there and the amplitudes and all that sort of stuff, and to do the resynthesis. There's also subtractive synthesis within the digital realm as well. And in here, we're just using digital filters instead of analog ones for more precise timbre control than what we would see in analog. There's also something called physical modeling. And this is synthesis via things called exciters and resonators that are based on real or fictitious instrument properties. And it requires heavy computation. So we won't really be talking too much about physical modeling in this class, but just know that it is a type of digital synthesis that's in this analysis-based world. There's also another thing called formant synthesis. Again, something we won't dig into too much in this class, but it's interesting. It is a way to simulate vowel sounds via complex filtering and, in a sense, be able to synthesize a voice. So if you think back to Max Mathews and Daisy Bell, this is sort of a modern way and a digital way to do what they did. Although I guess technically what they did was also digital. It was early computers, but a more modern way to be able to synthesize a voice. Now, all of these, or I should say digital synthesis, can also do amplitude modulation, frequency modulation, and ring modulation, as well as wave shaping type synthesis that we talked about in the last lecture with analog synthesis. Digital can do all of that as well. These are just some of the ones that are a bit different. Now, digital can also do something called wavetable synthesis. And this is segments of digital audio that are stored in memory and played back at different speeds to produce different notes. These segments often contain loop regions for sustaining sounds, and computationally speaking, they're very economical. They don't use up a bunch of resources and bog down your computer. So within wavetable synthesis, there's something called vector synthesis. And this is when values are interpolated from several wavetables, allowing for timbral changes over time. So for example, if you had 3 different samples, let's say a piano, a guitar, and a violin, and you wanted to do this, build this sound, you could have those stored in memory, and within a vector synthesis, be able to jump back and forth between the different spots within each of those samples to sort of paste together one single sound that actually changes over the course of the time that you're holding down a note on a keyboard, for example. Now, we also have something here called granular synthesis that exists within the wavetable synthesis. And this is when short, usually less than 100 milliseconds or so, bursts of, or grains as they're called, of sound, they're sequenced to create a longer output sound. Now, grains can be very simple sine waves or complex sampled audio files. And the variations in the grain amplitude, the grain frequency, or band of frequencies, the duration of the grain, the envelope of the grain, and crossfading between grains help to define the timbre and the texture of the sound. So we'll look at a couple of those examples here in a moment, but for now, we'll just finish up the basic part of this lecture side of things with a quick concept review, just the things we talked about the last few minutes. One, what is digital sound synthesis? The idea of an algorithm, know that. And know the synthesis types specific to digital only, so all the things in the slides here. So this would be things like the analysis-based synthesis, and we've got additive. Now, of course, this is sort of on both sides, but on the digital realm, of course, we've got things like resynthesis and FFT, which are specific to digital. We've also got subtractive and physical modeling, formant synthesis. And under the wavetable synthesis side, we've got vector synthesis and granular synthesis. So those are the things you'll want to be sure to retain from this lecture.